Hello and welcome in Science for Free channel, and this is Muhammad Alwi. Today we are still addressing the Einstein's photoelectric equation, which states that the energy of the incident photon, which is HF, equals the work function plus the kinetic energy of the released electron. Actually, this equation implies that there is a direct proportionality or linear dependence of the kinetic energy on the frequency of the incident photon. Because as we know that the Planck's constant and the work function of the metal of interest both are constants. So there is a direct proportionality from this equation, Einstein's photoelectric equation, there is a direct proportionality or linear dependence of the kinetic energy of the released photoelectrons on frequency of the incident photon. In other words, if we want to plot this equation, we can plot it in this graph. In this graph, I have three very important notes. The first one is about this value of frequency. Actually, we can plot in this graph the frequency of the incident electromagnetic radiation in hertz, in x-axis, and the corresponding kinetic energy of the released electrons or the released photoelectrons in the y-axis. And one very important point is it's impossible to plot this straight line from the origin, because plotting this straight line from the origin implies that we can release electron with zero energy photon, and this is actually illogic and it's impossible, because we need a certain amount of energy for the released electron in order to overcome the bounding energy with its atoms, or the work function. As we stated before, the energy of the incident photons, which is HF, must, as we already notice experimentally, must greater than or at least equal to a certain amount of energy, which is in this case the work function of this metal. This implies that the frequency must be greater than or at least equal to the work function of this metal divided by the Planck constant. And this is actually the threshold frequency, or the minimum frequency required for releasing the electron from the metal surface. So this is the first point, that we have to start this straight line from a certain positive value, not from the origin. And this value is the threshold frequency for this metal. And for each metal, there is kind of characteristic threshold frequency. This is the first point. Another point, also, by comparing the photoelectric equation, Einstein's photoelectric equation, to the straight line equation, or the first order linear equation, which states that y equal ax plus b, where a is the slope and b is the intercept. Putting this and comparing this equation to the Einstein's photoelectric equations, which is HF equal W plus K, or in other words, K equals HF minus W. Comparing these two equations, equation number one, which is the straight line equation or linear equation, and equation number two, which is deduced from the Einstein's photoelectric equation, we can deduce that the intercept, which is B, is corresponding to the work function of the metal of interest. In other words, we can deduce the value of the work function for the metal of interest from the slope, or simply by extending this straight line. Oh my God, it's very easy to determine this point as the work function of this metal in electron volt. This is the second notice. The third and the last and the most important one is the slope. Actually, also by comparing both these two equations, we can notice that the slope here is A in the linear equation, which is corresponds to H, or the Planck's constant. In other words, the slope in this graph, or in this straight line graph, is the Planck's constant. Yeah, so in other words, this slope is the Planck's constant. So in other words, if we have some experimental setup in which we can record the kinetic energies at different values of frequencies, or different frequencies of the incident electromagnetic radiation, such that we can plot this graph experimentally. In this case, we can find the experimental value of Planck's constant. And if this value, or the slope, equals exactly to the Planck's constant, this can be used as a direct and most straightforward confirmation of the quantum nature of the photon, or quantum nature of the light. In the next video, we will consider this experimental setup through which we can deduce experimentally this graph and plot it experimentally and deduce the value of Planck's constant, and hence confirm experimentally the Einstein's photoelectric equation, and more generally the quantum nature of light. Thank you very much for watching, and see you later.